In stats, we're starting to look at things beyond just the scatter plot and what effect observations have on predicted values. So last week we ended by talking about the correlation for the SEC football data. So it was this data right here from football season 2011. And this scatter plot right here, we ended the day by saying, let's change the color, that the correlation was 93.59. So that's positive and strong. We interpreted it on, it was Thursday or Friday last week. So they have a question in this thing. At the bottom, we found the correlation. Then they ask, what effect does Mississippi have on the correlation? And to justify ourselves. So when we're looking at this scatter plot, I've literally seen them ask before for the person taking the test to circle the value in question. And that's right there. You actually get points for things like that. So I've seen problems where they say circle the value in question, or then maybe add a dot, say this observation was added later, and they ask you to add it. And you get points for doing just that. So there's Mississippi. What if we were to delete it? So I would guess if we were to draw the trend line, the line of best fit through the data with Mississippi, I bet it would look, I'm just guessing right now, something like this. I'm just guessing. And then if we were to delete that dot, notice there's no dot down there to pull that line down. I bet the line would tilt and would look more like this right here. I don't know, that's probably tilted too much. I would go as far as saying Mississippi is not affecting the correlation. So I went into the calculator and, earlier with Mississippi, let's make that note, right, with that 93.59. This is with Mississippi. I deleted the Mississippi value and I got a new correlation of 91.86. This is without Mississippi. So yes, correlation and the slope, the predicted line, barely change. They do change, but I would say there's not a significant effect. So let's answer that last part. While Mississippi values, observations, whatever, increase correlation in other words, makes it stronger. It is not a significant effect. And I would back it up by, having numbers right there. It does say justify your answer. Many times on a free response, it says do this without calculations. So you're giving your best judgment. So use context. I would talk about things like it doesn't appear that it falls far from, here, let's write this out. Mississippi is not far from other observations. We're going to look at one in the very next scatter plot that is far. There is a very influential observation. So Mississippi is right in line with the expected pattern and also has a typical points per game. So this is not a significant observation. All right, so let's move on. And right here we have some printed formulas. I'm mainly just making you aware that on the formula chart, those 4 formulas are printed. So if you want to write next to them, so next to this is our least square regression equation. Another phrase I use sometimes is I call it the y-hat equation. Because notice the y has a little hat over it. These right here, we rarely use that formula. I've maybe used this formula once. This is for the slope. And you're using r and the standard deviation of y, standard deviation of x to get the predicted slope. Ooh, I should write that, the estimated slope. I've seen them maybe give you random other values, like a collection of these values, and they'll ask you to find another one. So it's like you create a system of equations based on those two. I honestly think they're kind of dumb questions because you're just doing random algebra. I mean, it's stats, but I don't know. It's just an excuse to use those formulas. Notice over here, this is the correlation formula. Technically, it's called, the correlation coefficient. I don't think you'll ever see it printed anywhere, but this is technically Pearson's correlation coefficient. You don't really need to know that. You just need to know that's the formula for correlation. All right. And we'll go from there. So speaking of least squares regression equation, we started talking about it. And before I even got into this slide right here where it talks about y hat and the predicted value of y, we actually just dove right into this problem here, this Gessel scores, a score you get at the age whenever you first learn to talk, first spoken word. So what we did was we drew a scatter plot. So maybe hit pause, draw a scatter plot, and enter this data into a spreadsheet. Here is my scatter plot right here. And there's all the data. So what we need to do, we got our scatter plot done. We need to calculate R and the least squares regression equation. So first off, I'm going to point out this value down here is an influential observation. Big time. It is way far away from the rest of the data. This one is also kind of influential. That's not a technical stat word. But I will say, I mean, that value, you know, if the one on the far bottom right was gone, that one I wrote kind of on, it's influential. It's pulling the data down. Both of those dots combined really influence the linear regression to a negative relationship. It's almost like it pulls the line in line with that final one. And you'll see in just a moment what it looks like. Without those two dots, If those two dots were gone, if you're only looking at these, it does not look very negative. Not a lot is going on with that data, which is why this is so influential. If we were to delete that value, I bet it would drastically affect R. All right, so let's jump to the calculator. I typed in all the data. Let's run linear regression. I picked the fourth option because it uses B for slope. I named it A and B. And here's our data. So notice this is the slope where you see the cursor. It is negative, and this is R. Notice they have the same sign. They should always match. The slope and R should have the same sign, because this is telling you a negative linear relationship, and this is telling you a negative slope. They should match. So maybe copy those down on your paper. When I see that data, I write it like this. I'm going off of, let me write it at the top of the screen. I'm going off of, let's use another color. Y hat equals A plus BX. So I'm plugging into that. I don't want to use X and Y. I want to use age and score, because that's the X and that's the Y. So I write it like this. Score hat, that's our Y, equals the y-intercept minus the slope, because the slope was negative, x. But I'm not going to write x, I'm going to write age. And that is our least square regression equation. So make that note if you need to. Least squares, I always say square singular, but technically it's plural. And I'm writing on the scatter plot because I want you to be able to see the scatter plot, but that's down on part B. Then they ask us to plot the line. We need to draw that equation. Plot the line on the graph. I'm going to add to that. Use 2 points when you plot this line. We are not going to guess. I need to pick 2 ages, plug them into the equation, and plot the line. So I tend to pick the most extreme. So score hat equals 109.874 minus 1.12699 times the youngest. When I plug all that into the calculator, I get a predicted score of 101.99. When I plug in the highest age, like I said, I like to pick the 2 extremes. You can pick any x's you want, but being that I sketched this graph by hand, you know, my scaling could be off. I think it's good to pick the 2 extremes. That way it kind of pulls a good line through the data. For 42, we get a score of 62.54. So that dot is a touch higher than that red one right there. And the 7 dot, I think, is a touch lower than what really happened. Yeah, a touch lower than 113. So like right there. And then draw a line through it. And that is our least square regression line and equation. Please show work when you do that. Use 2 coordinates. Do not guess. All right? Use 2 points when you do this. be very clear in what you're doing. All right, that was all we did today. See y'all later.